Alright, hello team. Welcome back to part 2 of the world's longest video on cool lists, maps, and depth first search. Um, we went through in great detail all that you might have to do to implement some type of map structure for an adjacency list, to read in a graph structure from standard input, and then do a depth first search to visit all of the nodes. And where we had left it, check out that video if you want that in-depth view. But where we had left it was where we had this output here, where we were getting this kind of weird ordering, like we weren't sure what was going on. In theory, we had borrowed this graph from the DFS article on Wikipedia. In theory, at depth first search, we should be like visiting them in the order in which the numbers are, but we don't seem to have that. And maybe we want to. Like, it would be nice to actually have it be properly ordered. And so there's a couple of things that we'll want to notice. And the first is, for every element for every entry in our map, the associated element lists are in reverse order. So they're like created reverse to the order in which the elements were inserted. Now that's basically a property of the way that the list insertion works for our list structure from scratch, right? So if you've been following along either in some of the other videos or in the previous video, that's just kind of a property or an oddity of the way that our list data structure works. We'll take a look at that real quick, just to kind of explain that. In our insert method, what we're doing is we're always creating a new node at the very beginning of the list, and then we are updating the next pointer to be whatever was already there. And so this is kind of like almost like a push operation for a stack. We take the existing list and then we put a new entry on the beginning of it. And so this has the property of when I insert a bunch of elements using this interface, the list will be in the reverse order when I finally get it. The most recently inserted element will be at the beginning of the list. And maybe now that could be fine, but maybe I want a sorted list. Maybe I want to make sure that I'm traversing elements in numerical or alphabetical order. That might be relevant for PA1. And so maybe we should think a bit about sorting. Now, the first thing is, so when I run this program, the output that I'm getting right now is the out string expressions that we put in for the DFS implementation. So if I go back up to our DFS implementation here, remember we put it inside the main class as a method. DFS takes a graph, a visited list that grows over time, and then a vertex to start from. In our implementation here, we had a bunch of out strings, but in reality what's happening is over time, we're adding nodes to the visited list and then returning that. So maybe the first thing I should check, just to make sure that I'm doing things properly, is to actually do something with the return value here. Right, so DFS is returning a list, and so maybe I should do something with that. I can create a new let binding for it, so a new variable, basically. So I'll say, I want my visited list to be a list that gets the result of calling DFS, and then what I'll do is visited list is now a list, so I can call our print method on it that we implemented last time. So let's see what that does. And it does nothing. Or alternatively, we're the order in which we visit the nodes, this is the order in which the elements are getting added to the list, and then it's reversed at the end, so it's like double bad. So maybe we want to actually address this by having some type of sorting mechanism. In particular, one of the things that's happening here is implicit in this DFS implementation is that we're visiting the leftmost children first, and that the leftmost connotes some sort of numeric value. And the issue is when we're doing our recursion, so like when we start off visiting element 1, our depth first search first encounters 8, and so it goes to 8 first, and then it goes to 12, which is how we see it here. And so the part of the issue seems to be, well, maybe we should be inserting elements into our map in sorted order. So how are we going to do that? Sounds like in our class, remember, going back to our map implementation, the elements are stored as this list. So in our list implementation, maybe what we want to do is to modify or perhaps add an insert method that is conscious of the order, so that it will sort of sort for us as we insert things on the fly. So maybe we should do that. So maybe we'll have a sorted insert method. So sorted insert, and again, depending on if I want a sorted list, I can just interact with it using this interface, as opposed to the original insert interface. And that will that way I can construct a list that's either sorted or not, depending on what the use is. So I'll just have another function here, same signature. So sorted insert takes a string as a parameter, produces another list as always, and we're going to have some additional logic in here now to make sure that new S gets put in the correct location relative to the other items that exist. And so we need to think about a few things that are going on here. So just to help you visualize again, if I wanted to have the list A, B, C, the way that is kind of represented here is I'll have a list node with A, whose next pointer is another list node with B in it, whose next pointer is yet another list node with C in it, whose next pointer ends with this nil list object thing right at the end. Now, if I wanted to insert D, in fact, well, sorry, let me change these letters real quick, just to make it easier to contrive some examples. BDF. All right, so DF. All right, so I suppose that I want to insert G, so I want to put something in at the end. Well, the way that that's going to work with the original insert method is it's just going to pop in a new list node. So it just immediately creates a new list node and then appends the existing list. So the original behavior would be, I'm going to create a new list node, and then I'll just copy all of this other stuff in as the next pointer to that new node. I don't want that anymore. I have to be more conscientious. I have to be, aware of the new element's placement in the existing list. So how is this going to work? Well, I want to traverse the list until I find the list node whose current string comes after the input string. So I want to make sure that I go through the list until I find the very first element where I know my new element should come before it. And that's where I'm going to put in my new node. So how's that going to play out? Well, so if the new string is less than, so if the new string comes before the existing string, that's when I'll put in, so create a new node, attach the rest of the list at that point. So I keep recursively inserting until I find the very first node that the new node should be stored before, and that's where I'll create the new node. And that new node's next pointer will be the remainder of the list at that point in the list. So so that's part of it. The other part that I have to be aware of is nil, right? So if I'm on an empty list, or if in this example, for instance, if I'm trying to insert G here, I'm going to be at the end of the list, and I'm going to encounter this nil at the end, and I need to put in the new list node before that. That's kind of the normal. That's kind of like the case that we had before here, where we would just do one of these things. And indeed, I may just borrow this line and say, if is nil, then do that. Otherwise, then I need to do this check. If new S is less than S, then I need to do this again, right? So this is where I'm going to put in the new node, right? So I want to create a new node, and then all of the current stuff gets put in as the next pointer. So the rest of the list that comes after this point gets put as the next pointer. I put the new string into a newly created list node object and just return that. And then as I recurse back up the call stack, this new list node will be appended as, or like updated as, the next pointer for the parent call. So this will eventually find its way into the overall list itself as the recursion finishes. So so that brings us to the next case. So if the new string comes after the current string, then I need my recursive call, and so that's what's going to be here, right? So otherwise, recursively call insert on next, store result in the next pointer. So what's going to happen is I want to call next.insert of the new S, and this is going to return a list that needs to go into the current next pointer. So I'll update the next pointer to be that, and then I'll also return self. So I'm going to update the self node's pointer, next pointer, with the result of inserting the element recursively. So I'm basically skipping over the current node. I'm not touching what's currently stored in it, but I'm going to update the next pointer to be a new list, whatever that new list is, that should contain the new element after it's finished. So that's what's going to happen here. I will finish that if, and so now I should have a sorted insert method that I should probably test. So we'll come back down here, or down at the end here after our attempt at depth first search. Before I change anything about the map and the way that the edges are interacting, I just want to check this sorted insertion on its own. So I'm going to create another list. Let sorted list is a list type that is a new list in, and I'll just have a block with a bunch of insertions. So let me do sorted list gets sorted list dot insert. And let's put in, some random, letters and see what happens. And I need to print this at the end. Syntax error. It is unhappy with code that I wrote. It is probably totally reasonable. I need a then. That would help. 309. Oh, I need a left arrow. Not a Boolean comparison. All right, great. So it still seems to be. It would help if I actually used the method that I just wrote. All right. Now that I'm using the method, let's see. Still does not seem to be in appropriate order. I probably know, since I did it here once. Yes, okay, great. So we would like the insertion, the recursive insertion, to also be sorted. That would help. All right, this appears to look right. Let's make it even easier for ourselves and just use, D, E, A, C, F, B. Letters that are closer to the start of the alphabet. A, B, C, D, E, F seems right to me. All right, so it seems to be inserting things in sorted order. That is great. So now that we have a working sorted list implementation, now we want to use it in our map. In particular, we want to address this issue here, where elements appear to be in the wrong order. That, again, in depth first search, if we're trying to, visit nodes while maintaining the traditional tree ordering, we should be cognizant of that when we're doing insertions into our map. And so let me just find references to insert that are used in the map. All right, looks good here. All right, so elements.insert. Remember, elements is our a list here, right? So this is the list of children nodes for the current key. And so here's where we want to sort. We want to make sure that elements that get put into the elements list are sorted. Let's see if that helps. All right, so now we seem to have made some progress. 278, 3645. But what's this? 12.9. What could be going on? And we're almost there. But we have this weird thing where 12 is coming before 9. And the issue here is, let's go here and realize source and destination are string, comment in the video. What's your hypothesis? The reason that this is happening is when we're doing our sorted insertion, we have this comparison here for string. This is a string, right? So we're doing a string comparison. This is alphabetical ordering, or in this case, when we're dealing with these numbers, it sees the 1 first. 1 comes before 9, therefore 12 comes before 9. That is the way that strings get sorted. But not to worry too much. This isn't too big of a deal. What this means is that either we could change the implementation to have ints. That's entirely too much work and totally unnecessary, especially since the assignment mentions alphabetical order explicitly. We instead can rewrite this wiki thing so that it instead has letters. So why don't we just pull out the thing that I wrote before this video, where I have, like 1 is replaced with A, B is replaced with 2, etc. So I have the same graph here, but now it has letters instead of numbers. Maybe that will make it happy. Yes. No, still not happy because I specified the start node as 1 when it needs to be A. Now that we have letters here, so we're starting at node A, and look at that, we are visiting them in the correct order now. And now, one last piece, and that is that remember, the purpose of sorting was to ensure that we were maintaining this tree ordering when we were introducing our graph here. The other thing, the issue though, is in our depth first search implementation, we want to respect the exact order in which nodes get inserted into our list. Now, because that matters, and so it's almost correct. It's just backwards. And so now, instead of a sorted list, now maybe we want a reverse ordered list, so that we can insert things and not have this weird behavior where cool puts the new element at the beginning and then appends the existing list to the end. Maybe we want to make it so that the new element actually goes to the end of the list rather than the beginning. And so maybe we'll just do one more reverse insert method. Reverse insert. So reverse insert. We're going to take in a new string, as always, and we are going to produce a new list. Now, this will be a hilariously inefficient solution, but, for this assignment, totally fine. It will be hilariously inefficient because I'll just borrow this list here. So suppose I want to insert some new element. So just say Z. I'm going to put some new element at the end. The issue is I need to recursively traverse all of the list nodes until I get to the end. And then I need to put the new node there. And so that's going to be a linear time insertion, so linear time for everything. It's a totally bad way of doing things from an algorithmic perspective, but it is what we have to work with. We could, in theory, do some crafty stuff with maintaining a tail pointer and then having some type of wrapper list where there's a list inside of it. That would technically be more efficient, but, you know, like I said, for the purpose of this assignment and this example in Learning Cool, this is totally reasonable. So how are we going to do that? Well, basically what we want is to make sure that we're only going to insert the new node when we encounter a nil. So when we get to the end of the list. So that's easy enough. We can borrow some of the code down here and say, well, if we're at is nil, so if we're at nil, if we're at the end of the list, then that's where we'll put the node. Otherwise, tabbing somehow. All right. Otherwise, what we need to do is just recursively call insert on the next pointer. And so we'll say we want next dot reverse insert of new s. That will return a new, or that will return a new list, a new version of the list. Do we actually need to do anything with it though? I don't. Well, yes, technically we'll just update next to contain that new version of the list. Technically it shouldn't change because it will only be at the very end, so it should be updated. But we'll do that. All right, so we'll see how that works. So we're going to, like I said, if we get to the end of the list, that's where we're going to put in the new element. Otherwise, when we're at the if we're not at the end of the list, we'll just do a recursive call on the next pointer and try to insert at that point. So let us try that by visiting here and saying for visited.insert, let's do reverse insert instead. It does not like that. So now we don't really have any list. All right. So reverse insert. Oh, I see. That's why. All right. So we need to turn this into a block and return self. So we're updating. So we're doing the recursive call, and that returns the next pointer, but we don't want to throw away the current node. So we want to return the current node as well. So we'll just do that explicitly with this block. And look at that, now it's working, right? So now I have a visited list that is in the correct order for a depth-first search. So we have made it. It only took another 24 minutes here to make it to the end here. I hope that this has been helpful. I want to recap briefly what we've done. So we did a bunch of comments, so that's good. You should do that too to kind of write about what you're trying to do. In fact, we'll start here. So what we did was we came up with a graph representation. And again, see the previous video for more details. For PA1, you don't need edge weights, and so we had this setup where we just read in pairs of lines. And we can see that down here at the bottom where we have this these let bindings. So I do 2 in-string calls. So I read 2 lines from standard input, and then I have this loop where I keep doing that until I reach the end of standard input. And so we were able to read in a graph structure from standard input. We came up with some data structures to store this graph in a meaningful way that we could analyze with our program. So in particular, we came up with a list structure for storing lists of strings. Remember, Cool isn't that fancy a language. It is meant to be easier to compile than it is to write software in. What that means is the niceties of modern languages probably don't exist. So we don't have lists, we don't have arrays, we have to make them ourselves. So we came up with a list data structure for storing strings, like vertex names, and as well as several alternative methods for maintaining ordering. So we had an alphabetical ordering as well as a reverse ordering for inserting elements into that list structure. We used this list structure to come up with like an adjacency list, an adjacency matrix. So we had this map structure that we came up with that maps vertex names to lists of child vertices, so that we could maintain a concise representation of edges in our input graph. If I have input edges from A to B, then I'll have in my map the element, the key A, gets mapped into a list that contains vertex B. So we had this nice map structure for doing that, and we saw all of the different methods that we needed to build all of those things up, again, out of whole cloth. So from nothing, we built up these data structures. And then finally, once we had those, because the heavy lift was in these data structures, once we had those, then the DFS part was, 7 lines or something? How long was that? DFS, well, okay, so was that 20 lines? With a bunch of white space and debug code. So not too bad. Pretty concise representation compared to the other parts. Right? So in this list method, we had to hack together some things. We don't have null pointers in Cool, and so the traditional method of building an iterator and checking, is the iterator null or are we at the end of the list? We had to kind of hack that together using two different data types. We had this list class, which was kind of this abstract, empty, nil list that would represent the end of the list. And then we had this concrete list node class that was actually responsible for storing data. And that was nice. It allowed us to have this distinction using our isNil helper function for establishing, are we at the end of the list or not? That was how we got around that particular behavior. Now, again, there are other, if you're checking the other videos, there are other techniques that you could use here that don't involve using separate data types necessarily. There is an isVoid operator in Cool that you could use that's kind of like a null pointer. That's not quite the same, and I wanted to do it this way here because the other videos already covered that. But that's one engineering concern that we had to design around. We saw a particular idiosyncrasies of Cool where all of the attributes are private by default, and so if I want access to them from somewhere else, I need to have an accessor method. We saw how to build up functions recursively. We don't really have a for loop structure in Cool, and so we often replace traditional loop structures using recursion in this type of setup. And this is, by the way, is a staple of functional programming, where you see a lot more recursion to solve particular iteration problems. And so for computing something like size, what I would do is just say, well, the size is 1, representing the current element, plus a recursive call. And I just kind of sum up a bunch of 1s eventually, and that recurses up the call stack until I come up with my final a list size. And so that recursion took place in a lot of different methods. We saw it in everything from contains. So if we were searching for a particular element in the list, we would recursively call contains until we matched the element of interest or until we reached the end of the list. We saw that for printing, right? So if I reach the end of the list, I print out a new line. Otherwise, I print out the current element and recursively call print on the next element. This recursive behavior is a real common part of, Cool in particular, but is also common in other languages like that are more functional. So things like Haskell, JavaScript, or like OCaml or F#. Sure. So this is a common pattern in those languages. We saw how to deal with a lack of certain language features. So again, Cool doesn't really have a notion of customized constructors. You just get the default constructor, which allocates some space, and then it's up to you to have methods to help establish values. So in this case, every time we wanted to create a new list node or a new map node, we would call this init method to help us along, and that would actually populate it with real data, as you might expect from a constructor. We saw how, in comparison to a lot of other languages where you might do in-place or destructive replacements of particular data, we don't really have the same type of thing. Expressions in cool will return like new copies of things, and so every time I did an insertion call, like a call to one of these insert methods, it's conceptually returning a new version of the list with the new element inserted. I don't really update the existing list because every expression returns something. If I want to do something with that, I have to store it somewhere. And so we saw that play out with where every time I wanted to insert an element into any of these lists or any of these maps, I would have to call the insertion method, and then this produces a new version of the list that I then overwrite in the existing binding, the existing variable name. We saw other eccentricities like blocks, right? So every method, so every method in cool and every substructure of cool, so like if statements and while statements, everything is an expression, and it's always one expression. If I want to have a sequence of expressions, like I might see in other languages, then I need to create an explicit block of expressions. And that's, again, kind of this unique property of cool that will make parsing easier, but that is perhaps a pitfall that you'll want to be aware of, that if I'm going to add curly braces, that means that I'm doing a sequence of expressions, and I need to make sure that I'm properly delineating between them using the semicolon. So with all of that information out there, again, hopefully this was a helpful video, a sequence of videos, now that we've done this for over 2 hours. If there are, hopefully this will put you in a good place to start. If you have any other questions, feel free to reach out on the piazza or during class or office hours. Thanks, everyone.